presentation view, at least in PDF, could be problematic. Let's see, now we have that. So although it's not so nice to, let's see if it works if I start with the presentation mode here.
Okay.
So the title is instead Logic, Learning and Optimization of Cyber Physical Systems. I hope that sounds okay. Now, and then it does not work to make the switch. So I have to go back to, let's try one more time, because it's of course better if I can use that mode. Now, okay, finally.
Yeah.
So, based on that title, I would like to start giving a very short presentation also of my city. Just one slide here. You see that we have the sea close to us, and also a lot of vehicle industry. We have actually 3 main contributors. I mean, Volvo Trucks is the second largest truck company in the world for heavy trucks. Volvo Cars is not so big, but it's still significant, and especially for safety functionality, it has been world leading, you can say. And it's interesting, when I go to Australia, for instance, I have been transported with a Volvo bus. So my department is called now Electrical Engineering, and one of the divisions is Systems and Control. And when we give our numbers, we have the tradition to include also the PhD students, which makes the numbers significantly higher. So we could say that the seniors are more around 20 people in the division. I have stepped down now as the division head, but and I'm giving focusing more on education now. So we have one big master program in Systems and Control Mechatronics, which is, I think, quite unique, that you have 120 students at not an extremely big university, which takes courses in systems control and mechatronics. It also means that we have invested in a big new lab, which we call the Autonomous Systems Laboratory. And you see that we have both robot systems. We try to look at detailed mechatronic human interaction with robots, but also with autonomous driving. So this is a small commercial car, which the students can play around with and test their new facilities. Strategic research area, electromobility is of course a big thing nowadays, and we have some, especially the automatic control group is extremely good on controlling batteries, etc. And different aspects of AI. Flexible production is the area where I have worked mostly. We also try to establish activities in digital health and collaborative robotics. So the parts I will talk about are logical models and specifications, more methodology aspects, and then optimization. There will come up with some applications, energy optimization especially. And then some machine learning and reinforcement applications. So it's interesting when you go for go to industry and, for instance, Volvo trucks, there are so many unique instances and configurations in a truck. So they are even talking about 10 to the power of 100 truck instances. And how should you be able to make this product designed and configuration based on so many different versions and instances and flexibility? And there we have used some interesting new software for satisfiability solvers of logical, pure propositional logical expressions, and in that way given interesting methods and tools for Volvo trucks. In manufacturing, we are also focusing quite much on sequences of operations in factories, how to make that more systematic, how to get different views of operations from product view, production view, etc., to get a better understanding. So that was a little bit of a background, and now the question is, how can we support with some more basic methodology around this? And one thing is temporal logic, which is a logic where we extend also with temporal modalities like always, eventually, next state, etc. And here are some examples, and let me just show you always P, eventually P. It means that the empty circles here, a sequence of states, the empty circles can be anything, but sooner or later you must, in the eventually P, have got a P in a state, and that is a label then in that specific state. Another interesting property is always eventually, and that means that this P state must be repeated. So infinitely often you should go back to a state which has the property P. Then another tool which we are, at least some of us, are finding quite interesting is Petri nets. And for Petri nets, you can say that you have tokens which are going through this sequence of places. And Petri nets are very good to describe the flow. But the logics around it, in this case, resources that are shared between these different flows, they could be, let's say that you should have 5 or 10 such parallel flows. Then it should be a lot of arcs back and forth. And as a very famous professor, when I described this, he said, "Oh, you mean the spaghetti?" Yes, he's from Spain. And the solution to this is something I proposed myself, and that is to introduce Petri nets with shared variables. In this case, I introduce logical variables representing these resources. And to be able to make this transition A1, I need one R1 token. So that means that R1 is decreased from 3 to 2 if I make this transition. And then later on, I have an R1 plus, meaning that I give that token back to that resource. And in this way, you can more have texts describing what you are considering. In this case, maybe 2 robots, R1 and R2. But you can also have longer text, and in that way, with this plus and minus means booking, plus means give back. You can get the flow, where I think Petri nets are very useful, but the logics can be then described more by shared variables between these different sequences. This can actually be extended to also include continuous variables. Traditional state variables, and then you can even say that the derivative of one continuous variable lies between 1 and 2, so we can even have differential inclusions. To this we can also make reset of continuous variables. We can have guards on them and combine this with the discrete models I showed you before, and in this case we get what I call a hybrid or a cyber-physical system model, which is very general And you could, of course, argue then, well, isn't it too general? But we think that it is good to have a general framework, and then you can make different specializations for your different purposes, specific purposes. Another aspect is that something we have worked very much on is complexity and how to reduce the complexity. I used to give this question, which I also did 10 years ago. Aparajita told me that. And that is the locking alarm system. So I used to ask my students when I start the course, how many different states do you think there is in a locking alarm system in a modern car? And it's about 1 billion states in a BMW, at least, which we have analyzed. And to analyze that system and find if there are some situations where the system gets into what we call a deadlock, nothing more will happen, or a live lock, meaning that it just go around, but it will not reach the goal state. Then we use some reduction techniques, which is complementary to more traditional computer science method like satisfiability solvers, binary decision diagrams, etc. So here you see a number of transitions, where these tau transitions are invisible, from no connection to the rest of the models. So this is a local model. Then you can join these. And it's enough to say that, okay, you are either in 1, 2, or 3, but the visible A event you need to take care of. And then you can also have state labels, different state labels. In that way, you can also reduce that, and you may have combinations of this. And I don't have time to go into more details on this, but this is a very powerful tool. And especially that you can repeat this for the local events in the first model and the local events in the second one, and then join them, synchronize them together, and then you get more local events. And if you apply this the whole journey, you can, in the end, come up with a very small model. And the interesting thing is that by the reduction I propose here, this so-called branching bisimulation, then all the temporal logic expressions, which we normally are interested in, they are actually preserved. So just to show you an example here, this is a situation where we have a couple of resources, and we also have a buffer in between, or buffers in between. This can be described very nicely by Petri nets, but also can be boiled down to automata. And that means that you book or add a piece into this buffer, and you take that away to the next resource. And all these elements are synchronized together. So it could be an arbitrary number of resources and arbitrary number of places in the buffers in between. And then I also add a specific specification, which is here by meaning is generating a problem, namely a deadlock or a blocking system. Now, if you make this reduction, including these local events, in the end, you get this simple model. So from, say, 1 million of states, in the end, with the reduction, you only have 3 states. And then here we can see that, well, the goal state here is to get back to this state 1, and you can rotate here. This means more the working situation for the resources. But unfortunately, there is also an option that the system can go into this state. And from this, there is no transition back to the goal state. And that means that this system is not appropriate. And then you have to remove that. And either you point out where the problem is, or you can even make a synthesis trying to, by modifying your system model, simply remove that deadlock state, which could actually be a number of states, because these are abstractions of the state space. So that was a little bit on the logical side. Then let's go for the optimization. And here I come with a practical example. which we have worked for quite much on. It was actually initiated by our colleagues were working at that time from General Motors in the US. Based on a discussion with them, we suggested we started to look at how to synchronize robots together at the same time trying to minimize or reduce the energy consumption. And we can say that energy, it costs extra in terms of energy with rapid accelerations, heavy brakes, and unnecessary stops, and those should be avoided then simply. So here I show you a movie, and it has some sound, and maybe I can let that move down. Here you see the original programming of a KUKA robot, and you see some peaks here in the energy consumption. And then with our optimization, with our energy optimization, you get the red curve here, and you see that it goes much slower, or much lower, sorry. Then I put these two solutions on each other, the original and the gray and the optimized in color. You see, it's not that big difference between them, but we save during the same execution time about 20 to 25% energy. And when we showed this for KUKA, they said, no, this cannot be true. It's something wrong you are doing. But we evaluate this extremely much, and in the end they accepted that yes, we have something here. So what we do is that we record the trajectory, the path, and then simply we look at the path and try to see how we can modify the update sampling of that path. But before I come to that, you could just see that the difference between the two solutions is that you go more quickly up to a constant velocity in the traditional one, while and the acceleration is higher and then goes down to 0 and then goes negative in the original solution, and the optimal one goes up and then continuously goes down here. So you could say that this corresponds to a constant jerk instead. So not so much difference, but it still gives significant reduction. And even more if you then also introduce stops and waiting times. I will come back to that in another video. So minimize the trajectory accelerations, avoid long range waiting with high loads, and moving slower instead of waiting for zone excess. Those are, and also it's possible to change operation sequences. To look at the coordination between different robots, we generate the zone where each robot is moving, and then we take the intersection between the zones for the different robots. This is a zone generation for the right robot, and you do the same for the second one. And in that way, you can get the intersection and have the shared zone. And then only one of the robots is allowed to go into that shared zone at a time. And that means that you also have to typically stop in front of that zone entrance, but instead you should go slowly to reach that zone and avoid waiting and then just passing without stopping. That's another important aspect. And the time optimal and energy optimal, here you see that the sequences, when you look at the individual operations here, could be a bit different, and those are also involved here in the optimization. Here I have not a physical robot, but an animation in our robot software, the CAD software. Here you see that the robot now collide with each other. So then we should identify the collision zones, and then you generate these zones and make the intersection, and then go into our software called Sequence Planner. And then we try the new solution, and let's see what happens then. Then they had to wait a little bit, and we got 25 to 35% reduction. So this is for robots. We think we have a unique solutions here. General Motors, they were not so impressed, because they said, well, okay, robots do not use so much energy, but for instance, Daimler, they showed much more interest in this, and that meant that we have had a big EU project on this topic together with Daimler, KUKA, and some other companies and universities in Europe on this. So then optimization from more a mathematical point of view or methodology and tool point of view. What can we do and what can we use? And then you could say that there are a number of different areas, operation research, where you have a lot of interesting tools like linear programming, mixed integer linear programming, mixed integer nonlinear programming. In artificial intelligence, we have A-star, taboo, genetic methods. And constraint programming is a part of AI, we can say, where there are extra focus on the logic around optimization. And then even more into the logic area is that these SAT solvers, which I mentioned before, satisfiability solvers, there is one tool, SMT, and another one called Z3Opt. And Z3Opt has included also optimization facilities like branch and bound. I mean, they have brought up some of the well-known procedures from the other areas. So all four methods, they include search, inference, and relaxation. And the idea is to use the best you have from all these four areas. And then you could say that this last one is, at least from in some applications, very efficient. Here I show you some typical scheduling problems where the number of solved instances with Z3 you see here was the best compared to some other. Groovy is also very good software with the best methods from operation research, etc. And even more with this Z3Opt, when you formulate your optimization problem, your mathematical program, you can do it in much more readable way compared to OR methods where you use big M, etc., which can be a bit mess when you look at the formulations. So this is something I strongly recommend. Then when we have continuous paths, how can we handle that? Well, arbitrary, we can introduce Lagrange approximations, Lagrange polynomial and approximations on that. So we only satisfy the solution in discrete points instead of all points, but still we are able to introduce continuous differential equations into this. And in nonlinear optimization, that has been told for quite a number of years. And what we do now is that we can also include mixed integer nonlinear program into this by the discrete sequences. In our robot application, actually, we did something more simple, which I just briefly indicated earlier, because the idea is then that we have a given path, and the engineers have designed that. So industry, they don't want us to change that. The only thing they say, okay, it's okay if you change the velocity and acceleration profiles. So then we record the trajectory, the path, and then we can make measurements, approximations by Euler approximations for both velocity, acceleration, and we can even look at jerk. And then we, from the beginning, had a basic sampling period. It was actually 11 milliseconds in the KUKA robot. We call that now time unit 1. And then some of these intervals can be shortened because there you have low velocity. Here you have high velocity and acceleration, and then you need to extend that sampling period instead. And by that technique, still having the same final time, we could actually, and then generate that problem into designing the optimal sampling times. That was then an NLP problem. And then we optimize an approximation of a pseudo power, which is the product of acceleration and velocity. And in that way, I think I skipped this. We can actually, here you see the power for a movement here. It's a movement nearly 1 minute. And the original solution here has quite many peaks, while the optimized one has much lower peaks. And it means that we definitely can save energy, but even more, the power peaks, which the reduction of that we get for free with this solution. So this was a little bit about optimization, what we have done, and then I will go for some ideas around machine learning. And I shouldn't say that we are, I mean, that has not been our focus for more than 2-3 years, like many other groups. It's a new interest. But some of my colleagues have done still already some quite interesting applications specifically for our car industry and for Volvo Trucks. So as I guess most of you are familiar with, we have unsupervised learning and we have supervised learning. And in this case, we also have digital twins, a copy of the plant in a digital version. And then, of course, the idea is that we should have a digital twin that is as good copy as possible of the real plant. And also we need to sort of say synchronize these and to see that the digital model is always updated. And the thing is that now things are changing very quickly in a manufacturing factory. So deviation by frequent changes to the physical plant is actually a demand. And here the idea is that we make frequent point cloud models of the physical plant. This is actually possible just by mounting big number of cameras mounted under the roof of the factory. So this was an idea that came up 1 or 2 years ago. Then there is a problem here that, okay, let's say that Volvo has about 10 to the power 5 different parts to be detected and tracked in the factory. And deep learning algorithm needs, say, around 1,000 different images in various contexts of every object type to be able to recognize. So it's not possible to do like that, to just take the photos in the factory. So we need to have some training for this. So, but what you can do then is to use CAD files to synthesize artificial images that can be used to train deep neural networks to do object recognition. So take your CAD files, create artificial images, and based on that, train your network. And that is something we have tried also for object classification. So machine learning on 1,000 synthetically generated images for different backgrounds. And yeah, I mean, this is shown to work reasonably good. Of course, it's a number of challenges around this. And we have also worked together with our image processing group on this. So then some words on reinforcement learning. And reinforcement learning is the third big group of learning methods, which suits our interest in the control field, of course, much more, because actually this idea on reinforcement learning, we had more or less already 30, 40 years ago. And I gave a course on adaptive control for the students, let's say 25 years ago, with the idea that you have a process you want to control. You take some feedback from the process, try to identify the behavior of the system, and then you have a controller or an agent which you modify to improve the performance of the control process. So this is a feedback loop where you try to identify in this case for reinforcement learning, you try to get a criterion which you can then update in different states and see which is the best state to stay in to get the best reward. So feedback from the process, maximize reward by making good decisions. An agent learns from past experience. And yes, this is adaptive control. But okay, it has of course been developed in interesting new directions also with the huge initiative that has come also from the computer science community. Actually, in our control field, we have tried adaptive control for a number of years, and there were big enthusiasm on this, especially in Sweden, because adaptive control was quite much developed by my colleagues down in Lund, it's the southern part of Sweden, by a very famous professor, Carl-Johan Åström, and his colleague Björn Wittemark. And also ABB had some adaptive control facilities in their big control software. But to be honest, it did not fly. It didn't work very well in the end. It is so difficult to get these adaptive controllers to work in practice. And there are many different reasons for that. So adaptive control is not so popular at the moment, while reinforcement learning is very popular. But remember, there is a big difference, because reinforcement learning is mainly used based on simulation models, and it's much more focused on applications where you are still staying in the computer when you're doing the learning work. And I think that is the big difference compared to adaptive control, where you more or less directly go out to the physical system, and that makes it much harder. So but we have still tried to see if we could use reinforcement learning also for physical plants. And before I come to that, just give a very quick formulation of reinforcement learning for those of you who haven't seen that before. So I expect that you have heard about dynamic programming, which is a very generic optimization method formulated by Bellman like 70 years ago. And the idea is then that you have an immediate reward plus an optimal reward or loss function in the next state. And then you have also a weighting or forgetting factor there, gamma, which means that as we are looking more forward in time, we are not taking that so much. This gamma factor is typically between 0.9 and 0.99. So it gives the horizon in the future, how long time in the future you really want to consider in your optimization. And then based on this combination, you try to optimize among the possible actions of this function. And the interesting thing is that this next state here, we assume now that we have a model for that, which we don't have in reality, but we assume that now. And then we have that function gamma j star of delta of x comma a, and then we have a function which is a function of state x of the current action, and that function, the argument here, we now call q of x comma a. And that means that we should now maximize this q function with respect to the possible actions in state x, and the optimization of this gives you the optimal behavior or the optimal criterion. So this is a modified Bellman equation, and you get the optimal action by trying to get the optimal A out of this Q function. Now this Q function can actually be, as we see up here, we can replace this J star by the maximum of Q in the next state. And now, instead of having the original Bellman equation with the loss function or the criterion function, we have an update function based on the Q function, where you both have state and action. And this is the famous Q function that is iterated in reinforcement learning. And what we will try to do is to learn this function, because in reality, we don't have the delta function, but we replace that with observations from the plant. And we also don't have the reward function, but we get rewards from the plant. We assume that we can compute rewards from the plant. So this means that we have now, okay, this was a model-based Q function, and then we replace delta with x prime, the next state, rho, with the resulting reward. And then we have something that is now closely related to the physical system. So what we do is now, simply since we don't know this Q function, we only know actually x, a, x prime, and r prime from the physical system. The current state, the action we can take, the next state, and the resulting reward from the physical system. But we can iterate this equation, including an estimation of this Q function. And then we have, from the beginning, we take mostly focus on learning based on this equation. So we take a lot of information from the next reward and the actual state. And after some time, we have better knowledge, and then we can more trust also on the current estimate when we should estimate the next Q function. So then we have this learning rate, which from the beginning is close to 1, and then it goes down over time, and you trust more and more into the current Q function. So then the question is, how should we choose this alpha? And there are a lot of proposals on that. And the most simple one, and the one that comes from the stochastic derivation of this, is just 1 over k. But that means 2 quick reductions. So there are some slower reductions that are proposed. So the model-free updates of the Q function stored, they are stored in a lookup table for all x and a pairs. And well, this technique is limited then to, say, 10 to the power of 4 to 6 state action pairs, which is then quite limited. But that is still a possibility in some applications. But then there are approximate solutions to this. For instance, one way is to introduce neural networks, and then we are talking about deep reinforcement learning, deep neural networks. But there are also other more simple approximations that can be used also for this purpose, and there I've referred to the literature. Okay, here the Q-learning was actually based on a deterministic model assumption, but it's interesting that even if you start with a stochastic system based on Markov decision processes, you get in the end exactly the same Q-learning function. So this can be then applied together with a digital twin. Why? Because I said that in reality, we cannot make thousands of iterations before we have some for a physical plant, because then it simply does not work in reality, because when we try around we get a lot of bad solutions, and then we should have bad production for a long time, which is not okay. But if we have a digital twin, that could be actually a good starting point, and you could simulate in the digital twin and to get a good starting solution for this Q function. And in that way, we could also hope to get, say, in 50 iterations or something, we can get improvements. And that kind of the idea we have used in a so-called smart assembly process application, where we have plates that are well together, and it's about the geometrical quality of those type of plants. So I think that is what I tried to say on this picture also. We have this expert device in terms of the digital twin. So then, of course, there is a difference between the digital and the physical system. And here is an illustration where red means bad geometry quality, but after this online adjustment, just locator, clamp joint parts, and scan the assembly, and based on the current scanning, you modify your state, and that means that you then adjust your locators, and after the optimization, you can get a better geometry, because blue means good. So that was my presentation and summary. Complexity handled by incremental reduction. That was what I shown in the beginning based on this branching by simulation. Combining basic logic and smart search for efficient optimization based on this Z3-opt is another interesting alternative and complement to more traditional operation research methods. Energy can definitely be reduced by optimization, and there we had an interesting proposal based on a given path, and then we tried to adjust the sampling updates to be able to reduce velocity and accelerations especially. Vision and machine learning has an interesting and great potential. And we can improve this digital twin by reinforcement learning, and also the online update of the physical plant. There, it's also an interesting aspect, and then it is to just focus on the deviation between the model and reality and try to learn that deviation model or that delta model. That is an idea we have not developed yet, but we have talked about that for some time, and I think that will soon start that activity. So since I'm talking about automation, I used to give this final comment. We should not only automate the production, but also the planning and implementation of automation solutions for sustainable production. In that way, we get automation 2 times, or the square of automation. Yes, this is thanks to some of my colleagues. Konstantin has worked on this reinforcement learning more recently. Sarmad worked very interestingly with the robot energy consumption together with Christopher, and Martin and Knut are my colleagues as seniors in the group. Thanks. And yeah, okay, I should have a slide on questions, but that we can take in any case. So that was, and it was exactly, I should have 50 minutes.
Oh my gosh. Session optimization here too.
Okay.
So thank you so very much, Professor. You have given an overview of what your research group is doing.
Yep.
May I request participants to, if you have any questions, any points of discussion, please feel free in unmuting yourself. And I can see Vinay Nasaji, you would like to ask some question, Vinayji? No? Anyone else who would like to ask a question?
If you don't have any questions, I have some more material, but let's see first.
Okay. I have 2 questions I wanted to ask you. So while using this optimal path, you have used Lagrange's polynomial interpolation, perhaps, Lagrange's polynomial. Have you also used some kind of geometric splines for, as we know that if you take geometric splines, then there is a better, for path planning, it can be better used. That's what was my.
Well, okay, I would say, I must say that first, this is a topic where we definitely are not expert. I think that what we brought up then was the idea that in optimal control, these Lagrange polynomials are quite common. And I think also that the coupling to the differential equations is quite nicely described with this Lagrange polynomial. But I mean, definitely there are other options here. And in fact, this Lagrange polynomial was only used in another study where we looked at Tetra Pak. You know, they are making these small packages for milk and so on. It's also a Swedish company, actually. And Tetra Pak, they are there. We looked at the packaging machine, and in that case we used the Lagrange polynomial. But that is a very limited experience we have. So yes, there could definitely be other spline solutions, for instance, that are better. So if you have some applications or publications on that, I would definitely be interested to get your results on that.
Okay, thank you.
Yep.
So we have done some work on path planning, not exactly for optimization, but because we have some experience on geometric splines, so definitely we'll be in touch. The second question that I have, you said that adaptive control in case of it's with reinforcement learning is a difficult nut to crack. So I used to think that the cars that we have, this autonomous vehicles, are they not using reinforcement learning for adaptive control, or am I? I have maybe.
That's an interesting comment, because I'm not sure if I should buy a car which is fully trusted their autonomous driving on reinforcement learning, I would say. Okay. But in the end, I mean, there are, of course, always a lot of security functions around this. I will have an interesting examples on how things can go with security functions and autonomous driving when we go for the last lesson with the students. But I would say that now reinforcement learning, I think, is mainly used for learning how the car should behave. Mm-hmm. And how the driver behaves. You know, it's not so easy to always get, so to say, a nice driving in the autonomous way. And therefore, there is a lot of activities trying to learn from experience how drivers are acting and doing things. And based on that, to learn a behavior which they try to implement in the driving functionality. That is actually the only thing I know about this and what I've heard. There are other optimization procedures, something called model predictive control, which is in that sense, I would say, a bit more stable. That is also used for instance, looking at controlling the distance to the next car and to move from in a crossing from one lane to another, and etc. I will at least show you one picture on that also when we come to the lesson. And there it's more of standard optimal control in a smart way, and you could say model predictive control is the big thing right now in automatic control. So I would say that reinforcement learning is okay. Yeah, there is one situation where you can use it, I think, and that is for say energy consumption, because that is not safety critical in the same way, and then you can learn how do the vehicle consume petrol, and in that way you can see, okay, now he did it in that way, and now we'll make it in another way and see if we can improve something. And in that way the reinforcement learning could also improve what you have studied in your simulation. So it's, once again, all these learning methods, you start in a simulation environment. And based on that, you come up with something, and then you because I mean there are a huge number of good simulators for the behavior moving with trucks and cars on the roads and etc. So you must start with that, and there you also use the reinforcement learning in the simulation environment, and of course in especially for energy consumption, I think you can use that also. In the physical system, yes.
One last question.
Yeah.
You told that there can be billions of states of transition from in this what do you call
locking alarm
system. Locking alarm system.
Yeah.
I was wondering, how do you analyze each and every possible transition using this logic? I mean, it's in a small setup. Mm-hmm. It is easy. So for this, is there any kind of automation that you do? How do we analyze these very large possible states and very large network?
I mean, the one thing is by this abstraction that I mentioned, and you. Then you could say that, okay, you have some goal states, and they can be maybe abstracted into one state, and then you have some initial states, then typically only one state, and then you have the huge number of other states, which you could then, in the end, when you have taken care of all local behaviors, you can actually boil them down also only to a very few number of states. Then you also have the bad states, and they are also grouped together, but because you don't need to have it was interesting that in this Volvo car software they found an error where the problem was that it was an error in many states, But yeah, it sounds very bad, but actually it's not a big problem. They solve this and they have procedures for this. But it's interesting that you could have many bad states, but they also only grouped into one block state. Mm-hmm. You have one bad block state, you have one goal block state, you have one working block state, and then you have the initial state. And in that way, when you have boiled it down to that, you can easily see what kind of properties you have. Maybe you don't have any bad state. I mean, that's the goal. You shouldn't have any bad state. And then for this locking alarm system, the result will be that, yes, in the end, you could see that, yes, you have a bad state. And this buffer system, which I mentioned about resource buffer, and somewhere I had introduced a deadlock. And in the end, I only had 3 states.
Yes.
And it's exactly the same characterization. I can put temporal logic expressions. They are equally valid for that small model and the huge model, which is quite a fantastic result.
Thank you so much, Professor, for throwing light on this. Any other questions if you have, participants?
Yeah. I would like to continue with the question you asked.
Yeah, that's...
Yes. Sir, since in locking alarm system, you said there are billions of states, and which usually reduced to few states using state minimization technique. So as we know in automata theory, we cannot write a program to design an automaton. Am I right? So it has to be designed manually.
Mm-hmm. Okay. That's
confusion is, how do we actually design such a huge automaton, since it cannot be designed automatically?
Of course. The thing is that for this locking alarm system, I think that if I remember correct, the number of basic automata are about 20 or 30 or something. And you could just say, take 10 two-state models. I mean, just on and off, 10 two-state models. How many states do you get then? You get 2 to the power of 10. So that means around 1,000 states. So the idea is that, okay, you have, this is component-based, this is modular based. So you have a number of quite small modules. I mean, one is from one software, another model is for another software. Of course, all the physical equipment have their small models too. But when you then combine all these small models together, it blows up to this big thing. But still you have a point, because for instance, for this lane change system in the autonomous driving, which I will mention about in the last lecture, then they said that when they analyzed that software, I think it was like 200 lines of code. And that is not easy to transform to automata. But if you introduced variables together with your automata, then it's actually not so difficult to translate. I will show you an example of a simple MATLAB code, which can be easily translated to this extended finite automata. So that is a reasonable technique. But even that is sometimes considered to be too hard. And then you come once again with these learning facilities. So there are, for instance, a method called L-star, I think, which tries to learn also automata modeled by learning techniques. And you can say that reinforcement learning, for instance, is also based on you go in one direction, you try a transition, and then you go in another direction, etc. And in that way, you build up the state model. But the thing is that, I mean, most people are thinking in the same way as you gave your question, namely that when I say 1 billion states, they are thinking about one automaton with 1 billion states. But that's not in our mind. it's totally interesting. It could be actually, we are analyzing system with 10 to the power of 200 states. It's more than the number of atoms in the universe. But we can make, sometimes we can make that very fast, because that means that we are able to use the structure of the system and these reduction principles, etc. I hope that give you at least some flavor, but very good comments, and also Aparajita, your questions were very good. Thank you.
Thank you, Professor. So I have stopped this recording to start the new recording. And with this, would you like to take a small break before we go ahead with the?
Could we just take 3 minutes?
Yes, sure.
Yeah.
Participants, we are going to share a feedback form with you. Please do fill out the form and submit today.
Ma'am, I have already shared.
So you have already shared. I'm sorry, then I thought that is not shared. Thank you. Thank you for sharing.
So also we request you, if you have registered in GAN portal, I think 6 of you have registered in GAN portal. There also you can give your online feedback.
Is it a must, Shaban, or they can or they may not? I mean, what is mandatory?
They should give feedback.
They should give.